think I figured out. Welcome to the stream. I think I figured out YouTube. Hopefully, pretty soon we'll start seeing my content starting. It is not. There it is. Okay. All right, so it's just about 10 seconds behind. I think we're all good. 10, 15 seconds. All right. I'm going to close that and we'll get started. Over the last few weeks, I've been kind of polling to see whether I should be on YouTube or on Twitch. A lot of folks followed me on Twitch, but honestly, I have more subscribers on YouTube. And folks are saying that they go to YouTube for programming content, not Twitch. So I think is a pretty wise choice. We'll see how it goes. The experience from me personally is a little bit different, and I'm sorry to bore you with those details at the beginning of the stream. I had a little bit of, snafus getting started. It's not just a one button click to start streaming. You have to click multiple buttons, etc., yada, yada. The announcement, the preview that shows up in your feed, if you're subscribed to me, looks pretty good. So I'm pretty happy with that. If you are in the channel, please do say hi. And pretty soon we'll get started. We'll get started doing some coding. Let's see. So, reminder that last time we were working on the nursery. Or rather, we started working on the nursery in HanoiDB. We've been doing HanoiDB for the previous 4 weeks, and we had mostly focused on, can we read existing databases that were written with HanoiDB, and can we kind of understand the format and try to read and do the typical stuff that you would do with an immutable database. So now we're going to get into some. When we started last week, getting into some territory that I haven't personally been in before, which I think is kind of exciting, because what good is a database if you can't write to it? And HanoiDB has a really interesting way of operating. I did mention that it is it's based off of LSM trees. So an LSM tree, the idea is that, the log of your, LSM means log structured merge trees. So the idea is that you log updates to the database, and then over time you merge them together as those keys that you are updating don't get rewritten. And it's really good for, the technique was invented for spinning disk drives, but it's actually quite good for SSDs as well, surprisingly. So HanoiDB, again, is unique with respect to LSM trees. Other LSM trees you may be familiar with are like LevelDB, RocksDB. There's one other that I've forgotten. I can't remember off the top of my head, but they're very much focused on kind of a tiered storage. You write Cassandra's SS tables are LSM trees. You write into different levels of files. As one level gets too big, it gets merged together and promoted to a higher level. And so forth. And finding keys in one of these databases means you start at the lowest level And as long as you don't find that key, you can keep going to higher levels to find it. And so then what we can do is really handle write heavy workloads very effectively with very little locking, and then your your reads are not as heavily impacted because you don't have to wait on writes to complete. So that's kind of an overview of the LSM tree style of database. HanoiDB, I mentioned it's unique. So what it does is it says, yeah, we're going to have an LSM tree overall structure, but we're going to do two things. The contents of each level is going to be a B tree, so that you get that sort of efficiency of finding keys. You think about other sorts of LSM trees. LevelDB doesn't have a tree. It's a sorted string table, but it has skip lists. So a skip list lets you jump to a particular part of the file. So SS table means sorted string table. A skip list says it's sort of like a compact tree. It says if you want to look for this key, you can scan to this part of the file. And so it keeps really tiny miniature trees almost. And then, you do 1 or 2 or 3 levels of the skip list to find a key to start scanning from. But being a B tree, HanoiDB says, well, we're going to start from a root block. You'll scan or maybe even bisect that block if the structure is correct, until you find potentially either the key itself or a pointer to another block that the key is potentially in, and so it does the B tree thing like we saw in BerkeleyDB. The other thing that is really unique about HanoiDB, and I don't want to ramble on too long about this, for this is about coding, but this is just to catch you up and also to see if people will join the stream on YouTube. Anyway, so the other thing that HanoiDB does is it amortizes the cost of merging levels with writes. So rather than writes being kind of disconnected from merges as they are in LevelDB, and like having other threads specifically focus on merging from time to time, what HanoiDB does is says, okay, every time we get a write, let's check whether we should trigger merges. And then every level, when it reaches a certain threshold, every level is kind of triggered to do a certain amount of work toward a merge. And so you kind of spread the cost of that merge across all the incoming writes. This potentially is, has a bit of throttling to write throughput, but it's sort of like automatic back pressure, right? So instead of being a thing where I'll give an example from like back-end programming that a lot of people use. You've got a very unpredictable and bursty and high throughput producer of events. Often what you'll do is you'll put a message broker between that and the thing that needs to consume those events. Why? Because that message broker can absorb the burstiness, and you also decouple the producer from the consumer, so the consumer can be scaled independently of the producer. Now, the flip side of that problem is that your queue can overfill, and that's something you have to actively monitor. Well, it's a similar idea in in like HanoiDB versus these other LSM trees that do their merging on a separate thread. You've basically disconnected the source of the work from the thing doing the work when you have a separate thread specifically focused on merging that kind of operates independently of the input. So HanoiDB says, let's connect those two with a source of back pressure. And that source of back pressure is, all right, every time you try to write a key, you may trigger a merge. And every level may be instructed to do a certain amount of work when it hits that threshold. So that way you kind of, you do slow down operations potentially, but you don't run the risk of having too much work in the queue that you can't catch up. Okay, so that's part of the philosophy of HanoiDB. The two things that are distinctive, that incremental merge work and the B tree inside each level. Okay, I think I've ranted on long enough. So our stream quality is looking really good so far. So let's go ahead and get started. If you want to follow along on the GitHub, let's flip over to this scene. This is the repo where we've been doing the work. I realized I haven't added a README, so maybe we should do that first at the beginning of this session, and then we'll return to doing the nursery. And the nursery again is like the bottom level. The what is it called in Cassandra? I think it's called mem tables. So there's a log, write ahead log, and a mem table in Cassandra, and this is a similar idea. We keep a B tree map in the nursery, and we have a disk log for each entry. Okay, so so this is, you can follow along Sean Cribbs HanoiDB-RS on GitHub, and let's go ahead and make a README real quick, which I'm really shocked that we didn't do, but let's do it. Okay. HanoiDB-RS. And implementate, and this is going to be dumb right now. HanoiDB. Creston Crab. HanoiDB in Rust. This is not released on crates.io, so I'm not going to bother with that right yet. But for design, documentation, please refer to the original repository. Okay, easy enough. And let's commit that. Okay. And we'll push. If my Git aliases are really confusing to you, let me know later. I will share them in the chat because they're a thing I have in my fingers. And when I don't have them in my fingers, I use LazyGit for that particular thing, especially interactive patch building that is really bad in the original porcelains. But LazyGit does it pretty well. I do miss Maggot. I think Maggot was way easier than LazyGit. But LazyGit is a pretty good substitute. Okay, and at some point we're going to have to refer to the original code. So let's review what we did last time. We started this nursery file. We created a nursery struct. And it contains a file handle, which is the write ahead log. It contains a directory which it's writing to. So this will also be used when we write out the contents of the in-memory to a B-tree file. So that's where we'll write it. It has a min level and max level. So these are configuration things that we'll use eventually to refer to the other levels that need to be given merge work. And then we have the data for the nursery. Hey, Chris, welcome to my YouTube stream. Thanks for coming. Okay, so we have a B-tree map, and the reason I'm doing B-tree map is that when we want to go and write these keys out to a file, we want to make sure they're in order. So we will we'll figure out how the original Erlang implementation does that write out. But for now, it's important that they're ordered lexically by their keys. And then we have this value enum, which is we need to record tombstones. In a traditional B-tree database, you might put a deleted entry into a file, but it's especially important in a system like HanoiDB or like LevelDB that you record tombstones so that when you find a key, you can know it doesn't exist, and that this, if you find it in a lower level of the database, then you don't have to search the deeper levels of the database, the bigger levels of the database for this key, because it's been deleted. So it is important here to have, some kind of enum that wraps the in-memory data, which will be searched first. There's a whole thing with timestamps and we haven't handled that yet. HanoiDB has some really interesting things with timestamped entries, so things that can expire, but we haven't handled that yet in any of our code. Okay, so we have the data. We have the total size that we've written. So this is going to be basically the size of each of the encoded entries. And then the step is like how many steps we took in terms of writing. And this is how many merges are done. And these are basically copied from the Erlang implementation. We haven't really made use of these things yet. But so when we create a new one, we get the directory, we make it an owned path buff so that we can hold on to it. And then we figure out that the file is, we name it nursery.log. This is exactly what the original, you can see it's a little faint there, sorry, but the original nursery.log over here in this HanoiDB test directory that we generated in previous stream. And then we're going to, so we have a to-do here. We need to deal with recovery. And so we're going to have that be a separate task that we go through. But for now, we're going to assume that the log file does not exist. So we'll create new and make it append only, and then we'll open it. And this will return an error with the question mark operator. This will return an error if the file exists or if we can't open it for some other reason. And then we return this data structure. So we've got the nursery created from given the directory and the min level and max level. So what would we do when we add an entry to the nursery? We give it a key and a value, pretty easy there. And then we create an entry. So this is the entry enumeration that we did when reading. And I think I had some open questions about like what is the actual format of that. I think if we switch to memmap2 crate, this will become more unified. But for now, we clone those into the entry, and then we call the encode method, and this will turn it into that format that we've been reading from the file. We can jump over there in a moment when I finish talking through this method. And then we insert it into our data. So we're saying, take this key and this value and put it into the B tree map that we are holding on to for memory. And then we write the entry to the log, and we force a sync on it. So this is fdata sync, essentially. And yeah, and then we record the size of this binary entry into the total size. So this will be influential when we want to decide now is a time when we need to flush this data to a file, and then like tell the next level to absorb that data file, and we can start a fresh log, a fresh B tree map, etc. This is a part where in the original implementation we needed to invoke that incremental merge that I talked about previously, but we aren't doing it right now. And then we record that we did one step. So this is the sort of trigger, this, incrementing the step. Like when we reach a certain number of steps, we should trigger the cascading merge. And if that worked, we return, okay of the empty tuple. I think before we go, on, I think I would like to make delete. I think in Rust it's, let's see, B tree map. So get, it's usually called remove. So maybe we'll make it remove. And this will take mute self. And then we'll see if there's some, because there's going to be, we'll see if there's some overlap between these two, and we'll maybe make a private function which, takes some of this information and handles the file stuff for us. Okay, so key, and here we could use a slice. Honestly, I wonder if we should change these to slices. No, let's make them owned. For now, I think it's reasonable to make them owned, because we're gonna have to clone them anyway to make this entry and encode it. But we are we need to have something owned to insert it into the in-memory data. So we either clone here or we clone outside. And in this case, we're doing both, unfortunately. But let's go ahead and kind of duplicate some of the stuff here. Entry deleted. Right. Okay. And we'll put key. Right, because we have to clone it either way. And then here a lot of this is the same, right? Except here we're going value deleted, and that has no contents for that variant. It does feel weird, given that these are like, the key. The key is borrow of the key type, right? Or rather, the key type implements borrow for the reference type given here. I just this feels like it would be more ergonomic, but we're gonna have ownership of the keys anyway, so we might as well pass it in here. We can probably do some improvements on that at a later time. Okay, so now what's the shared stuff? Maybe what we do is make a function which is we say with like it's not pub, it would be like write internal or something like that. And then this would be we need the key. We need the value, which is going to be value, and we need the bin entry, right? Which is also evacuate. Result. Okay. So what we'll do here is we'll go value. We'll do all that, and then we'll do that. Okay, so now we can replace this with self.writeInternal key value deleted, right? And that could just be the return value of that function. That's a lot nicer. And up here, we'll do something similar. And this will be value plain. Value. Okay. Good stuff. All right, so this is not going to work. I guarantee it's not going to work. Why? Because we haven't implemented this for deleted. Have we? Oh, we did. Oh, awesome. I think we talked last time about we can pre-allocate if we know the variant. Should we do that right now? It feels like a good thing to do. Yeah, so let's make encoded size. And this will return a U size, right? So pass shown comes through the code. I love it when I set up nice spots for myself. Yeah, it is pretty good. Okay, so we can compute the encoded size pretty straightforwardly. So let's do... Yeah, we have some things there that we need to figure out, but the other thing we could do, by the way, is... I think I saw it on some other data store I was looking at this past week that someone had implemented, and there were size restrictions on keys and values. We could do that, enforce that at the API, and just see if we could avoid, this particular source of unsafety. The other thing that we could do is do try into and make this return a result with a particular error, but that seems like a thing. Use try into and return result. That's something that we could potentially do. But let's go ahead and pre-compute the size. Okay. So we're going to match self again and fill the match arms. And we'll start with keys and values. So key value, if the timestamp, and I think what I'll do is I'll write this out as an expression where we account for every part of each entry. So if let's see. So we know we have 1. This is the tag. And then we have, if there's a timestamp, then we know as ref, because we don't want to consume this option. That's not what I want. Is it as ref? Let's look at option. I think there is, it's like if you have a borrowed option, you can turn it into an option of a borrowed. Is it as ref? Yeah, that's exactly what I want. I don't know why I was doubting myself there. So as ref map, and if you have anything, we don't care. It's for, and then we say on wrapper default. Nice little trick there. The default for usize is 0. So we're just going to do that. And then hopefully this will determine that it's a usize. Yeah. Okay. So if it has a timestamp, we need 4 bytes for that timestamp, which is a U32, right? We have the tag either way. And then we have 4 bytes for the key size. 4 bytes for the key size. And then we have the length of the key. Key.value. Okay. No, not key.value. Value.length. What am I doing? Value.length. Okay, and I can probably remove that tag right now. So I'm just going to put real quick here, documentation, tag plus optional timestamp U32 plus the key length plus key plus value. Okay. Okay, that was not too bad. That's a computation that'll optimize nicely, I think. Okay, so deleted. We have 1 for the tag, right? And then we also have this expression, because there's an optional timestamp there. And then we have the key length. And then this is actually probably the easiest one. Let me document this real quick. This is tag plus optional timestamp U32 plus key length. Okay? Plus key. And this one is easier. This is 1 plus 4 plus 4 plus key.len. This is tag plus block pause plus block len plus key. Okay, now we can go and say, rather than this, let's say vec new with capacity and self.encoded size. So now we pre-allocated the buffer to fill. And then we can just push our stuff into it, and this won't cause It's not likely to cause a lot, but it won't cause reallocations as we're filling in the data, which is a good thing to do. Cool, that wasn't too bad. All right. Okay, we're going to have to... And that popped up on the wrong screen. Okay, so here's the original Erlang code. We're looking at the nursery. This is an important thing that we should probably take note of. So how many steps can you take? Well, what's the min level? And B tree size is bit shifting, by the way. If we... my Erlang language server is still not working. If anyone knows off the top of their head how to fix that with sed, let me know, because I don't know. Yeah, so B tree size here is 1 bit shit left, that many levels. So basically 2 to the power of that level. Interesting. So this is saying... Okay, so the number of merge steps that should be taken is 1 power less of 2 to the min level. So if our min level is 10, so in other words, there's 1024 entries in the lowest level, then we should do 512 merge steps when we do an incremental merge. Okay, I'm going to make a note of that in over here. So let's put it here. Number of merge steps should be size of min level. So key size or key count of min level divided by 2. Keys is 1024, and that implies 512 steps. Okay. And I think I'll copy this just for reference. All right, so we will do that. I think there's some things we need to do with handling deeper levels than the nursery before we can really do. We need to implement the whole write the B tree right to the file, but that's going to be kind of complicated. But I think we should do recovery first because that's a straightforward thing to do for the most part. So let's read through what they do there, and then we'll implement recovery. And I'll go ahead and put a let's see. We'll make a recover method here, and this will be, you know, we don't know what it'll take yet, but it's going to return a result of a B tree map. And we're going to have to define... I'm going to make a type alias for this real quick. Type... let me call it nursery data. Okay. See if Rust Analyzer will help me here. Oh, I should have done that. Here, let's let Rust Analyzer do that for me. Extract as type aliases. Yeah, let's call it nursery data. Okay. So yeah, then we don't have to type that. Yeah. And there will be stuff here, so I'm going to put ... We don't know what it is. And Rust Analyzer is going to hate that. Cool. All right, so right, so recover. Let's look at this signature. So given a directory, top level, min level, max level, and config. It's just checking that the min level is less than the max level, that they're both integers. And then it's trying to see if this file exists. So if the nursery log, this is a macro to make sure that the name is consistent. If the nursery log exists, so that's what we'll return OK here, then it'll call this do recover and return a new nursery. If it doesn't exist, then it just proceeds with the new nursery. And I don't know that we can kind of do that in our Rust code. Let's start by saying we're going to pass this file name. So let's say a log file is going to be a file. No, we don't need to borrow it. We can pass it. No, this is going to be asref path buff, right? Impl asref. And then the question is, it looks like it needs all of this. The config, it's not clear yet. It needs... This is interesting. Read nursery from log. Min level and max level are passed to that, so we'll have to look at that. And then this finish function... is what closes the log and unlinks it, right? So we'll need something that cleans up that. And then it asserts that the log file is gone, right? So maybe we'll look at this finish thing. Let's go to read nursery from log. This is probably the part that we're most interested in. So it's like read the whole file, and then given the binary contents of that file, find all the keys that decode correctly. This is the part where we'll need to be making use of our knowledge of the entry format to make sure that we're syncing up and we don't have any corrupted entries. I don't know what this is. I guess this is like, this is a full read, and this is we found corrupted data, and so it's just logging. But regardless, we get the keys out. So this is sort of like a partial success. And then it returns the, like a new nursery struct. So we're not going to return a new nursery struct in this case, I think. Probably what we'll do is just return the data, and then we'll continue to construct the nursery, but we just won't have the default empty. So what will be interesting is we should return, if the file doesn't exist, we should just return OK and a blank nursery data, right? So let's say we need let's do it as an early return first. Return okay, default. Right, so here, if it doesn't exist, then we'll just return okay early. And otherwise, if it does exist, then we should try to read it. So read file. Can we just do log file read as ref read? Nope. I want to say there was like a read fully. No, it's just read. Okay. Okay, so the problem here... No, that just returns a bool. Okay. So we're going to say read. I'm going to say let contents. And, you know, there's a question here about whether we should, like, open the file and... and then, you know, read incrementally. The Erlang version doesn't. It just reads the whole thing. So I'm actually not that worried about it right now. The bigger, like, complete trees, you know, this is just a sequential log, right? The bigger complete trees are... like something that we don't necessarily want to read the entire file. But here it's going to be at most like 1024 or 512 keys or wherever we pick as the min level. So we're actually going to, let's go ahead and pass the min level, max level. And then yep. Now, the other thing we could do, I guess this is on Nursery. We could put this, we can't really implement without wrapping in a new type struct. Never mind. I was going to say, let's make this a method on Nursery data. Well, Nursery data is btree, so btree map. Okay. So now what we should be doing is let's look at our entry here. What's going on there? Did we mess up entry? Yeah, I think I was talking about generics last time. It doesn't have any generics right now. I think I was trying to do this, you know, parameterize it over vec u8 or slice of u8, borrowed slice, but it's not. Okay, quick fix there. We don't need the other, those two. Okay. Right, so now we should be keeping track of where we are in the buffer. And the other thing is read works on a slice, the read trait. We could probably do, I don't actually want to do that. I was just thinking like we could read from the buffer and have it keep track of the position. All right, well, let's say our current is 0. All right, so we need to basically implement we need to make entry read work on this buffer, or yeah, this is actually a rationale for using a file handle, because we already implement read on entries, and this returns, you know, self, and U64 is the length. I don't remember why we did that. I think it has to do with this iterator. Oh, right. Where to start from. That's an interesting to-do we should have to address. I think, oh yeah, so the reason why that is, these are offsets into the file. They need to be U64s. And this is like, we only want to iterate through one block. But here in the nursery, we don't actually care about that. We can just advance the file. So, okay, so let's say file, let mute file. We already have open options. And we're going to say read true I don't know that we need any of these other actual methods, so let's just say open log file. Okay, so now let's make a we're going to make something to put it in. And then let's do so this entry read returns a result. So what we can do here is we can say while let OK entry read, and we pass it the file. That is private. Okay, so we're gonna have to make that public. Public to the crate. Honestly, these are internals, and like when we get farther, we will restructure this such that the internals and the public API are separate. Okay, so while we are able to read an entry, let's match on that entry. Let's actually do this, and we don't care about the length for now. The nice thing about using this already is that that entry already handles the CRC checks, so we don't have to deal with any of this stuff. Yeah. Okay. And let's just handle all of these potential things. So again, we aren't dealing with timestamps, so we can kind of ignore that. We will have to deal with it later when we support that feature. But let me put a little note in here. Update this when we support timestamps. Okay, so then we're going to just put it into key, and this is value plain value. Okay, easy enough. For this one, again, we're going to ignore the timestamp, and we'll insert a tombstone. Okay. And for Poslen, this should be an exception because we don't expect to see that entry in there ever. One thing that we'll need to double check is that the format that we're encoding and the values that we're reading can do a round trip. So that's probably a good test to write. We should create a new nursery, add a key to it, figure out how to close without deleting the log, and then try to do a recovery. That's a pretty good test. And this should honestly be an exception. And I'm going to put unreachable here and say nursery log contained B tree internal entries. Okay, so now, yes, I know I didn't return the right thing. So now we've read all the entries, we can return data. That wasn't so bad. What's going on here? Oh, I don't want path buff, I want path. And it says this doesn't need to be mutable. Cool. Okay, and we're not using min level and max level yet. I don't recall what those are for. We'll have to look at their algorithm and see why. If that's just passing through to populate the nursery struct as it's created, that's fine. We don't need to handle that here. But if there's anything intrinsic about recovering the nursery data and then that involves the levels, I think we should look into that. Okay, so let's do the other thing that this needs to do is now we've read we need to drop it probably. The main thing here is I don't want to have the, I don't know that it matters that the file's open, but here we have a file that's just for read. Okay, so the file system, I want to unlink the file, right? Remove file. Okay, so this doesn't require a file handle. We might want to change this while let into loop, because I feel like it's important to potentially log out when you log to the console or something when you get a corrupted entry. For example, if there's no more left in that file, like a key or value is truncated or something, you'd want to print that out, or if it doesn't pass the CRC checks. Okay, but for now, let's do what was it? Remove file. And that requires a question mark as well. Log file. Well, let's do that. Sometimes you just need to add an ampersand and it's happy. I'm surprised this isn't like, it's a double deref. Whatever. Okay. We did import these things. I'm not sure whether we should go ahead and import some of these other, like, should I import remove file? Let's do that. Okay, so now what should happen is when we read the write ahead log, the nursery log, then we'll slurp all the entries out of it into the in-memory representation, and then we'll remove the file at the end. So we have a fresh log. We know that we've captured everything from that file, and so we should remove it and start with a fresh one. And then what will happen is this will create that fresh log. So now let's say let data is going to be self recover. Yeah, and I think we don't need this min level and max level. So let's just go ahead and get rid of them. They are pointless. This is not log file, this is file, and we'll borrow it. Okay, and then we can remove this default here because we have already recovered the data. Cool. Let's have a look at the Erlang implementation again and see if we can learn anything from it. Yeah, so the other thing that we need to do here is we removed the count thing. The total size we probably need to compute. We need to have a way to compute that. Which to me says we need something that tracks it here. So this should return result of nursery data and a usize. And here we'll do and 0. And here we're going to say total, and this needs to be mute. And we're going to have to make that public to the crate, the encoded size. Because remember we made a mistake down here. I didn't account for that. Let's fix that. And let's make this pub crate. So remember, every entry has to be followed by that tag byte of So I wasn't accounting for this bit here. And I think it's still incorrect because we need... Let's pull that out. That's a constant, right? So we're going to say 4 plus 4 plus 1 plus this. That's probably a weird way to do it, but all I want to say here is this is, we have the entry length plus the CRC32 plus trailing tag end. And then, you know, all this. Hi, Isaac. I'm glad you found the stream. Thanks for coming to YouTube. I know it's a change for everybody. It was a little bit dicey at the beginning. I messed some things up. They have a little slightly different workflow for getting started than Twitch, but it's been going pretty well. The stream output is looking good. So yeah, okay. So what we want to do over here is say encoded size. The other thing that we could do potentially, and maybe we don't need that, because entry read returns a U64, and I think we're accounting for yeah, so we're returning that here. I don't know why I'm bothering. I'm glad we went in there and on the, you know, the encoded size, we made sure that it was correct, because I was off by 9 bytes there. Let's just simplify that to 9. But we have this, so let's say size. Size as new size. And that one's probably safe because we're probably on a 64-bit architecture, but all right, and then we need to return data and total size. It's funny that I implemented that for the iterator specifically, that, you know, trying to read an entry would go, yeah, here's the entry that you got plus how much I advanced the file pointer, how many bytes, then okay, we do have an issue here. We are expecting tag end to be at the beginning. So rather than at the end. And I think that's the case for the B-tree files, each level. So we need to handle that in how we're encoding them. Or it actually doesn't matter which one. or we need to put this Sentinel byte at the beginning of the log file when we open it. Yeah, Chris might help. Actually, Chris, I don't know if you're still here, but you were a big reason why I switched to YouTube. I had seen your streams on YouTube. I was like, hey, this is actually kind of nice. And you know, then I pinged him on Mastodon. I was like, why do you go to YouTube instead of Twitch? And he gave me some really great answers. And so yeah, like, and then the polls were just kind of overwhelming. Everybody goes to YouTube for programming content and not to Twitch. Yeah, there were like only a handful of respondents who said they prefer Twitch. Anyway, here we are. We're doing a stream on YouTube. Okay. Let's see real quick. And the OBS is not real great in terms of the tools there. And now you're here. Yeah, you are here. I'm very grateful. Okay, so we need to figure out this feels like I need to make a decision. And I think the decision I'm going to make is, since this is newer code than the read side, I think what I'm going to do is I'm going to put the signal byte there. Let me see, entry.push tag end. No, this is wrong. Okay, so I kind of did this the wrong way, in a sense, because the encoded size for output we're going to say -9 there, and we're going to say total size, right? The other option is that we could because we need to know the entry length, right? Now the entry length, though, should be our encoded size -9. So maybe it's not that important to so we have these two allocations here. What I'm trying to think about is, should we instead of this, like allocating once and allocating again, should we instead just use this, push the tag on there on the front, push some bytes that will replace later. Actually, we already know the entry length because we computed it. We just have to replace the CRC. Now, this will have to slice. That's fine. You know, it takes a slice of U8. And then we can replace... Yeah, it's going to be a little bit more complicated, but I like this idea. Okay, so we're going to just do a vec with this size. And then we know... So that's with capacity. That doesn't have anything into it. So we're going to do... Oops. We're going to go ahead and push the tag into it. Because we want the tag to be in the beginning. We know the length. So I'm going to comment all this out, and we'll reinstate it in a bit. And we'll just return entry. So we know the length already. Let's see, total size minus 9, right? As U32. More parens. This is extend, so we want to extend it with 4 bytes. 2 BE bytes. Okay. And then let's extend it with... This is a stub for the CRC32, right? And I'll put a note in there that we need to do this. A stub for CRC32 or spot. And then these things can just push it in there, and you know, they will not end with the tag byte. They'll start with the tag byte. So when we go to read the file back, we'll actually sync correctly. And then down here we can slice. So 1, 2, 3, 4, 5. So slice 0 through 4. Slice bytes 5 through 9, right? And do the hash over the rest of it. Okay, so let's do we're going to say 9 to the end. And then let's see how we can replace a slice of the contents of that vec. We could do as mute slice. No. I mean, that's what we might need to do. Let's see. I want to see if there's something like replace. Something like not copy within. Not fill. I feel like this should be syntax level. Help me here, Chris. I just want to replace the 4 bytes with the contents of that CRC32. All right. You know, note that this is an interesting thing about how vecs are like a pointer to memory with a size and capacity. You'll note that the things that actually change the capacity are on methods on vec, and everything else is a method on the slice itself, and it derefs to that slice. Okay. Let's look at slice. I think that there's something that I mean, we kind of want to do this, but we want to copy or move those bytes that we create into there. Don't want to get mute. So yeah, I need to replace 4 bytes in an arbitrary. What I'm thinking is I should take a mute pointer. I'm just looking for the right method, if it even is a method. Not a mute pointer, a mutable slice of that range, and then set it equal to, maybe it's deref? I don't know. It feels like copy, mem copy. Here, limit to rest, please. Copy. No. Replace. This is what I want. Yeah. Copy from slice. That's, let's see, copy from slice. Yeah, thank you, Nishant Lem. Thank you. I think this we'll use this. So let's take that idea, and we're going to do let's go ahead and convert it to bytes. Let's say entry. And we want, I think it was 5 up to and not including 9, right? Copy from slice and CRC. Thank you. Thank you. I haven't done that many things like this where I need to go and like edit something after I've written it. The compiler likes that. Okay. Yeah, thanks a lot. And again, this is, you know, in terms of efficiency, we're trying to fill it from the beginning, and not reallocate where possible. Yeah, it is a literal mem copy. Yeah, I just was looking in the wrong place. Thanks for the tip. And you know, the Rust standard library is pretty big, and I don't remember everything all the time. So, okay, so now we've gotten our tag, our Sentinel tag at the beginning. So that when we read back the nursery log, it'll, you know, we can reuse this method we wrote earlier to read from a B-tree file. So, you know, we're expecting tag end at the beginning, etc. And now, I think our recovery should work. So what will be interesting? Let's go back to. I hope recovery will work. Let's go to our main file, and I think what we're going to do is, yeah, we're we've already established that we can read from an arbitrary file in this directory. Let's create a nursery, and for now, let's just implement debug on this. Let's see here. So this actually returns data, and did I say it was a U64 or U size? Yeah, total size. So we can replace this, right? And I want to see if we can recover the log from this one. I have some doubts, but we'll learn some things regardless. So I wanted to derive debug on this. This needs to derive debug. Yeah. Derive debug clone. Okay, so let's try to make a nursery. Fine. New. And let's say so reader. And we're going to say the min level is 10, as this one is. And we'll say the max level, I don't know, 25, doesn't matter. And we'll debug that. Okay. So this needs to return a result. And we'll do OK, just so we return a result there. This is maybe where we could use anyhow, whatever. It doesn't matter at this point. This is just our space to try out our API. Okay, so we're attempting to make a new nursery. Bottom level is 10. Top level is 25. Like, I don't know how big that is. That's a lot of keys. 2 to the 25. And let's see if we can recover that nursery. First of all, let's make sure we don't have any errors. Okay, so this has a result that must be used. I have a bug there, so we need to put a question mark where we're doing that right. Yep. Written amount is not handled. Well, let's use write all. Okay. Okay, now it's just complaining we have, you know, dead code. That's fine. Field 0 is never used. Are you kidding me? Never read. Oh, okay, okay. All right. Well, let's see if we can cargo run. Okay, so we did get a nursery. But it didn't recover any data. Let's look at... Now, the problem here is it removed that data. It would have unlinked that file. I should have backed it up beforehand. Yeah, so now it's empty. But it didn't read any data, but it didn't complain. I think probably what we should do is, when we're recovering here, rather than just doing this while let, we need to, kind of handle when this returns an error. So I would love to see what that problem was. Note that over here, when we're reading it, we are returning proper errors, but we're not we're just swallowing those in that loop if it returns error and something. Because it's potential that this, it could not read enough data, or it could be a corrupted entry. We don't know. Okay, let's go ahead and handle that in our recovery. So we're going to do, we're going to change this to a loop. Right? And we're going to, instead of the while let, we're going to do let okay. Let. Now maybe let's do match. And we'll say, oops, that's not what I wanted to pop up. And then we'll say entry size. And if it's error, what we want to do is we want to eprint line error reading and then we'll just break from the loop. Now, what is going on? Oh, we need to do, sorry, log file.display. Now, the asref, the potential problem here is we need to handle some errors differently. For example, here, if we can't read enough bytes, like if we're at the end of file, but it's, trying to read the header, then we just reached the end of the file. That's fine. But if we read at least a header, and then we try to read it and the data is incomplete, that should be a different error, right? Obviously, we handle the, we didn't find the tag byte. We didn't get a correct CRC32. There's a lot of cases to handle here. So I wonder Let's look at read exact. Yeah, this is an IO result. There's a lot of potential things here. I wonder if we can get at the kind. Turns a reference an inner error. I don't know if like handling this particular thing is going to be very helpful. There's kind. Okay, so we could potentially look at this enumeration. Yeah. Yeah, well, we have our own error types. The issue is what I want to... Maybe it's unexpected EOF we handle there. What I want to do is convert the IO error into something that has a bit better semantics based on where that error happens. Right, so I think I want to potentially create a new one here. Right, so we can make... So we have corrupted file, not incredibly useful. Maybe we want to say end of file reached. Let's just do this. End of file. Because I want to be able to match on that in the caller. The other one I want to do is say incomplete entry. And that will be if we can't read the entirety of the entry as it's specified with the length. Now, so here, like if we get this error, I want to be able to just bail and not worry about logging it. But if we get this one, we should say like, and maybe this has a standard IO error in it. Yeah. Okay, so over here, where were we? We're in entry read. Jump there, please. Okay, so if we're trying to read this, error.kind. I think if it's a we need to import that. Can you get that imported, please? Nope. Unexpected. We saw unexpected EOF. I could probably make this an if. Oops, does that implement EQ? This is non-exhaustive. Implements hash. Be really... It's surprising to me that it doesn't implement EQ or partial EQ. No, it does. Okay, so I can simplify that. Let's see if error.kind equals that. Then we're going to return end of file. Else we're going to return error into. So I need to, import that. What's going on? Helps if I save it. Okay, that's not really that elegant, but in this case, we know that if you can't read the header, the 9 bytes here, you might be at the end of the file. And in this case, down here, what we want to do is something similar. And except that we're just going to do error incomplete entry. Because we know that at this point, okay, it's telling me not to make a closure there. Just use the constructor. So we know at this point then, oh fine, whatever, that we couldn't read the entirety of the entry. And so we should wrap that. Now, there may have been some other error that happened. Maybe what we could do is do this. Let's go ahead and do that. Because I think any other error we want to bubble up. Now, in this case, we could potentially go and have that not contain anything. Although we may want to like print that out. Yeah, let's go with that. Else error into. Not real pretty, but let's see here. Note that we've got two things that have standard error internally, but this is just for the auto conversion. This is we're explicitly converting it, so it's not. It shouldn't be confusing. Hopefully, but yeah. Okay, so now over here in the nursery, what we can do is. Say something like only print it out but if it's an end of file, just don't print anything. patches. Bang. So this will handle IO errors. It'll handle our incomplete entry. And then if it's just an end of file, we'll still break. All of these times we should break if we encounter an error reading an entry. But in this case, there's actually like a corrupted nursery log. So I want to copy this nursery log over here so we can read it again. And let's run our program. Okay, so first part of the entry wasn't tag n. So now we've got, a problem with actually how we're reading it. You will note that that's back to 0 bytes. Let's look at so this one is 120K. Hex dump. What are your command line options? Hex dump. Interpret only length bytes of the input. Yeah, let's just do like 100 bytes. Okay, so we should see an FF byte somewhere. This is starting with all zeros, which is interesting. Remember, it's big endian. Let's do a few more bytes. Let's do 200. So here's a tag byte. It's interesting the nursery log doesn't start with tag bytes. So I wonder if what we need to do is I think we need to look back at the Erlang source and make sure that we are expecting the log to be in a particular format. If those assumptions that we made were wrong, because I'm seeing a bunch of 0 bytes here. No, I'm sorry. This is 4 bytes there. So that's the length. So there won't be a tag at the beginning. Interesting. So we probably need to change okay, we need to change multiple things. Over here, we did all this work to put the tag at the beginning when encoding. I think we need to not do that. I think we need to put it at the end. And this will be 4 to 8, not 5 to 9. And this will be 8 ... Okay, so this will mean that the sync point for this tag is on the end. Now, one thing that my buddy Greg told me for recovery was to read from the end. I told him, I wouldn't understand that. You're writing sequentially from the beginning. Why don't you read from the beginning? And I think his point probably had to do with these tag bytes. So you would know if you try to read from the end. You have the potential of knowing if it's truncated immediately if the last byte in the file is not FF. That's probably the basis of his argument. Now, how you actually seek back from there is another question. Do you just... Because FF could be the contents of a key or value, right? It's very possible. I think we can reasonably assume that what we need to do is put the tag byte on the end, and then when we're iterating over the entries, right? We should read 8 bytes here. There's going to be an issue of we need to, when we're reading the beginning of a block, we need to expect there to be an FF tag in there, and maybe we can do that as we are as we're loading the block. And what we need to do here is say last byte of entry wasn't tag end, and we need to figure out how to read just read 1 byte. The other thing we can do, actually, let's do it here. So the length, as you saw, is +1, and then we'll have it as the last byte. We're going to need to reevaluate all these other things because we're going to have the tag byte at the end. It's kind of making things more complicated. I suppose what we can do, actually, rather than changing that, we can make a vec of size 1 and read 1 byte. One. I'm going to say file.read exact. Mute tag I hate this. I need to think of a better way. And if tag 0, yeah. So this kind of gets the same thing. But now what we need to do, I don't think it's in the iterator. We need to, in the block, right. So we need to make an assertion that there is a tag end byte. And we're going to have to bump all these. Let's do 8 there, right? So if we do if header 7 not equal to tag end, then we actually, let's just do equals and do this the OK branch. Else return her corrupted file block entries did not with tag end. So right, this is where we're just asserting that there is that tag byte, and I want to double check this assumption in the design diagram and in the code. So down here, right, so we have a tag byte right there. We have the block length, we have the level, we have the data, which starts with the compression byte and then a tag byte, and then each entry is followed by a tag byte. So we were doing it the opposite way before. We were like, okay, this tag byte is the beginning of this entry, but we actually need to flip that because it needs to end with the tag byte. Saying repair recovery can scan for sequences like this to find all key values in a data file, right? So if a data file is corrupted, you can go, can I find something? I've never implemented one of these algorithms, so I don't know how bad it is. But can I find a spot in the file where there's this, 255 byte, this FF byte, a 4 byte length, and a 4 byte CRC, and then length bytes, and then another one like this. So I think it probably would have to do with like doing some searching for these tag bytes and then seeing if you can match that. That seems like a pain. I've never had to implement one of those before, so I don't know what it would be like, but at least if we treat this tag byte as part of the block rather than the entry, then I think we get the correct output. But I need to make sure that so we start at byte 8, that we skip the right parts. And it actually is 8422. It is 8 bytes. Yep. And now we actually need to make sure that we don't do this off by one thing, because they have to consume the tag end. So we kind of flip that. And now that we've messed all that up, let's go back to our main, and I want to like comment out this and restore this, because I want to make sure that with those changes that we didn't break the functionality we had working before. This is okay. Yeah. Yeah, okay, so I did some problem. 225. It's actually good that panicked. That's my bug. Oh, right, so these are all off by 1 now. So 0 to 4. And 4 to 8. Okay, so we've restored that with switching the tag byte to the end of the entry rather than the beginning. So that much should work now. And then let's copy that nursery log in again. And let's flip back to our nursery version. Actually, we can just run them both. And we'll have to scroll up. Borrow that there. And let's do some print lines in here so we get creating nursery. And then we will do okay. We're going to have a lot of output still. I just want to make sure that as we're doing this, we don't mess the other one up. Okay, going up here. Woo! Look at all those things we read out of the nursery log. That's our data, by the way. So there's the file, the directory, min level, max level, data, and here's our keys. So be able to read the nursery log. Yay! And truncate it. So obviously this is not safe yet. We should never read it and truncate it and never write out a new one. Because that's lost data. But for now, I think this is a good place to stop. So let's look at all of our changes. And we'll make a commit. Okay, so this was, we created the specialized errors. And I actually want to update that with one more thing. Let's go back to lazy it. Okay, so let's stage that. Yeah, I can't believe I left that. Oops. Go over here. Can't believe I left that generic in there and we didn't do anything with it. I committed it. That was funny. Okay. So now we are able to read entries from both, read entries uniformly, which is nice, both from the nursery log and from a file containing a tree. I don't like this. We can clean it up later. I think there were just going to be too many things to change there. And yeah. Yeah, thanks. Thanks for coming to the stream on YouTube, my first one. We're going to make this commit. Made some good changes there. Okay. So yeah, let's commit. This is session 5. And we are going to say this is implement recovery for the nursery log. We had to change how we are reading entries from the tree files as well, since each block, since block entries start with tag end, but technically individual entries only end with tag end. We also pre-computed the entry size, so we could reduce the number of allocations when encoding. That was good. And yeah. I think that's a good place to stop. Okay, and let's push. And that is up there. So thanks again, everybody, for coming. I'm going to wrap now. And we'll see you next week, again, on YouTube. And I'm sorry if you ended up going to the Twitch channel and didn't find it. We are on YouTube for the foreseeable future. Thanks again for coming, and we'll see you next time.